Load calculation is like packing a suitcase. You need to know how much weight power each item appliance adds before you close the zip. For each circuit, you add the power rating in watts of every device that may run at the same time. The basic formula is P equals V times I, where V is the system voltage 230 volts in most homes and I is the current in amperes. After you total the watts, convert to amps. I total equals sum of P divided by V. Demand factor DF accounts for the fact that not every appliance runs at full power together, just as you rarely carry your entire wardrobe on a single trip. DF is a percentage set by codes for each type of load. For example, 0.6 for general lighting, 0.8 for kitchen outlets. The design current equals I total times DF. This reduced value prevents oversized conductors and protects the supply from unnecessary cost. Example, a living room has two 100-watt LED lamps, a 1,500-watt TV, and a 600-watt socket outlet. Total P equals 100 plus 100 plus 1,500 plus 600 equals 2,300 watts. I total equals 2,300 watts divided by 230 volts, approximately 10 amperes. If the demand factor for mixed residential load is 0.6, design current equals 10 amperes times 0.6 equals 6 amperes. The circuit can therefore be protected with a 6 ampere MCB, not a 10 ampere one. Choosing the right conductor size is like picking the width of a water pipe. A pipe that is too narrow will cause pressure loss, voltage drop, and may burst overheat. The key parameters are current carrying capacity, ampacity, length of run, allowed voltage drop, and the material copper or aluminum. Step 1. Determine design current from load calculation. Step 2. Pick a base size from tables. For example, 2.5 mm squared copper, approximately 21 amperes for 30 degrees Celsius ambient. Step 3. Check voltage drop. Delta V equals I times R times L, where R is resistance per meter, ohms per kilometer, and L is one-way length in meters. The common rule is delta V less than or equal to 3% of supply voltage for lighting circuits and less than or equal to 5% for power circuits. For a 20-meter run carrying 10 amperes with 2.5 mm squared copper, resistance approximately 0.008 ohms per meter, delta V equals 10 amperes times 0.008 ohms per meter times 20 meters equals 1.6 volts, which is 0.7% of 230 volts, acceptable. If the drop were larger, you would move to a larger cross-section, for example 4 mm squared. Temperature correction and grouping factors, if many cables run together, also modify ampacity. Similar to how a crowded road reduces the speed a car can travel safely. Protective devices are the safety net that cuts the rope when a fault occurs. Miniature circuit breakers, MCBs, act like automatic doors. They open instantly when current exceeds a preset value, then can be reset. Fuses are disposable sacrificial links. Once blown, they must be replaced, much like a broken light bulb. Residual current devices, RCDs, detect an imbalance between live and neutral currents, leakage to earth, and trip within milliseconds, protecting people from electric shock. Selection steps. Step 1. Choose rating equals design current or the next standard size. Step 2. Pick type, B curve for residential lighting, trip between 3 to 5 times IN, C curve for motor loads, 5 to 10 times IN. Step 3. Coordinate downstream protective device should be sized smaller, so that a fault on that branch trips first, leaving upstream devices intact. Example, a 16 ampere MCB supplies a lighting circuit protected by a 6 ampere fuse for a bathroom extractor fan. If the fan faults, the 6 ampere fuse opens, not the 16 ampere MCB. RCDs are usually 30 milliamps for personal protection and 100 milliamps for fire protection. They are placed at the main board or subcircuits depending on regulations. Wiring methods are the various ways you can run the roads for electricity. The main types in a house are conduit, steel or PVC, like a metal pipe that protects the cables inside. Trunking, surface-mounted plastic channels, similar to a gutter for cables. Direct, buried or in-wall cables, cables laid inside walls or under the floor, protected by plaster or concrete. Cable types. Twin and earth T&E, two insulated conductors plus a bare earth, used for fixed circuits. Armored cable SWA steel wire armor, good for underground or exposed runs. Flexible PVC sheathed, for example NYM H07RNF, used for appliances or temporary connections. Color code UKIAC. Live phase equals brown or red in old systems. Neutral equals blue or black. Earth equals green, yellow striped. These colors are like traffic signs. They tell you instantly which way the current should flow, reducing the chance of a crash short circuit. Always check local code for any variations. Earthing is the safety path that guides stray current safely into the ground, like a drain on a roof that carries away rainwater. Bonding ties together all metal parts that could become live metal water pipes. Structural steel, equipment enclosures so they all have the same potential, like connecting all the gutters to the same downspout. Earth resistance R sub E must be low enough that during a fault the fault current I sub F is large enough to trip protective devices quickly. The relationship is I sub F equals V divided by R sub E, where V is the touch voltage limit, typically 50 volts for a fault on a 230 volt system. Rearranged R sub E less than or equal to V divided by I sub F. For a 30 mA RCD, the required fault current is at least 300 amps, because I sub F equals I sub R times 10, where I sub R is the residual operating current. Thus R sub E less than or equal to 230 volts, divided by 300 amps, approximately 0.77 ohms. In practice, many regulations target R sub E less than or equal to 1 ohm for residential earthing electrodes. Measuring is done with a fall of potential or clamp on earth tester, similar to checking how well a pipe drains water. A distribution board DB is the central nervous system of a house, directing power to all limb circuits. Layout basics. 1. Separate sections for lighting sockets, special loads, for example heat pump. 2. Group circuits by function and load size, keep high current circuits away from low current lighting to avoid overcrowding. 3. Place protective devices in a logical order: main switch RCD MCBS. 4. Reserve spare slots for future circuits, like leaving empty parking spaces for later cars. Wiring diagrams. One line diagram shows the main supply each protective device and the downstream circuits with their ratings. Use standard symbols: a square for the DB, a broken line for a circuit, and arrowheads for direction of current. Label each circuit clearly, for example L1 living room lighting 6 amps. This labeling is the house's map. It helps electricians quickly find a fault, just as road signs guide drivers. Fault detection is the process of finding where the leak in the electrical system is, similar to locating a pipe burst with a listening device. Common faults: open circuit, no continuity; short circuit, live touches neutral or earth; earth leakage, current flowing to ground. Testing procedures. Visual inspection, look for burnt insulation, loose connections. Use a multimeter to measure continuity, ohms, and resistance of conductors. A perfect conductor shows near 0 ohms. A broken wire shows infinite ohms. Insulation resistance tester Megger applies a high voltage, 500 volts or 1000 volts, and reads resistance. Values greater than 1 mega ohm are generally good. RCD test button forces a simulated leakage to verify it trips within 300 milliseconds. Earth resistance test, using fall of potential method, record the voltage drop between electrodes and compute R sub E equals V divided by I. Measurements should be recorded in a fault log sheet, much like a doctor notes patient symptoms before prescribing treatment. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Example 1, load calculation and conductor sizing. A kitchen has the following appliances: 2 times 1000 watts kettles, 1 times 2000 watts electric oven, 4 times 60 watts LED lights. Total P equals 2 times 1000 plus 2000 plus 4 times 60 equals 3320 watts. Design current equals 3320 watts, divided by 230 volts equals 14.44 amps. Apply a demand factor of 0.75, kitchen mixed load. Leads to I design equals 14.44 amps times 0.75 equals 10.83 amps. Choose a 16 amp MCB. For a 15-meter run, select 2.5 mm squared copper. Resistance approximately 0.008 ohms per meter. Voltage drop equals 10.83 amps times 0.008 ohms per meter times 15 meters equals 1.30 volts, 0.57%. Acceptable. Example 2, earth resistance. A house uses a single earth rod driven 2 meters into soil. Measured fall of potential. Test current I equals 10 amps, voltage between rod and potential electrode V equals 7 volts. Earth resistance R sub E equals V divided by I equals 0.7 ohms, less than 1 ohm, therefore acceptable for a 30 milliamp RCD. Example 3, RCD coordination. Main distribution board, 30 milliamp, 40 amp RCD feeding 2 subcircuits. Subcircuit a 6 amp MCB for bathroom lights. Subcircuit B 10 amp MCB for shower heater. If a live to earth fault occurs on the heater, current may be 150 amps, enough to trip the 30 milliamp RCD in less than 0.3 seconds while the 10 amp MCB remains closed, isolating only the faulty circuit. These numerical problems test the ability to apply the formulas and reasoning described in the earlier sections.